Welcome to the lesson on basic concepts of circles. At the end of this lesson, you will be able to define a circle and identify the interior and exterior of a circle. You will be able to define and distinguish between the radius, the diameter, and the chord of a circle. You will also be able to define and identify major and minor arcs, segments, and sectors of a circle. Meet Mr. A, a moving point. Right now, Mr. A has all the freedom to move in whichever direction he wants to. Let's see what happens if we restrict this movement a little. Meet Mr. O, a fixed point. We asked Mr. A to move so that his distance from Mr. O always remains the same. For this, we have joined Mr. A and Mr. O with a line. Do you notice any change in Mr. A's movement? The path now traced by Mr. A forms a circle. Mr. A's motion around Mr. O is the same as the motion of the tip of a pencil fixed in a compass. Using this depiction, we define a circle as a collection of all the points on a plane that are at an equal distance from a given fixed point on the plane. Here the fixed point is point O, and it is called the center of the circle. The length of the edge of the circle traced around the center is called the circumference of the circle. Let's draw a circle on this piece of paper. How many parts does the paper get divided into? A circle divides a paper into 3 parts. The area outside the circle, that is, the exterior of the circle itself, and the area inside the circle, that is, the interior of the circle. The circle and the interior area together comprise the circular region occupied by the circle. Remember the line we used to join Mr. A and Mr. O. This line is the fixed distance at which Mr. A moved around Mr. O. This distance is also called the radius. A line segment joining the center of a circle with any point on its circumference is called the radius of the circle. The term radius is used to represent both the line segment joining the center to the circumference and the length of that line segment. Coming back to Mr. A, he has found a companion, Mr. B. Both these points lie on the circumference of the circle. Rather than going around in a circle, Mr. A and B have found a direct way to connect with each other. The line segment AB that joins the 2 points on the circumference of a circle is called a chord. Mr. A and Mr. B have decided to move. The interesting part about their new position is that now the line segment joining these two passes through the center of the circle. Line segment AB is a special chord. The chord AB that passes through the center of the circle is called the diameter of the circle. Now, this special chord, called the diameter, has some very interesting properties. First of all, it divides a circle into 2 equal parts. Each part is called a semicircle. Another interesting part is that the diameter of a circle is equal to twice the length of the radius of the circle. A diameter also happens to be the longest chord of a circle. Remember Mr. A and Mr. B? Suppose there is no direct way in the form of the chord AB to move from A to B. How do you travel from A to B then? You can move along the circumference of the circle. The part of the circumference of the circle between points A and B is called an arc. Now, is there only one way to move from A to B along the circle? Actually, there are two. You can either take the longer path called the major arc or the shorter path called the minor arc. As mentioned earlier, a diameter divides the circle into two equal arcs called semicircles. How do you cut a cake? Well, one way is to just cut across it, like drawing a chord. Now, which of these two parts would you like to have? A chord divides a circular area into two parts called segments. The larger part is called the major segment. The smaller part is called the minor segment. You would obviously prefer the major segment as your share of the cake. A diameter divides a circle into two equal segments. Another way of cutting a cake is starting from the center and cutting it across two radii to cut a wedge. The region enclosed by any two radii of a circle and the arc between them is called a sector. The major arc forms the larger or major sector. The minor arc forms the smaller or minor sector. Welcome to the lesson on chords of a circle. At the end of this lesson, you will be able to prove that a perpendicular drawn to a chord of a circle from its center divides the chord into two equal parts. You will also be able to prove that equal chords of a circle are at the same distance from the center of the circle, and equal chords of a circle subtend equal angles at the center of the circle. One day, three friends A, B and C decided to have a race. They made a starting line ABC and decided to run to their common friend O. Who do you think won the race? A, B and C are all very good runners, but B won the race. Now let's see if B had any advantages. Aha! So B had the advantage of running the shortest distance, but they were all running from the same straight line. So, how did this happen? B ran along the perpendicular line from O to AB. The perpendicular from a point to a line segment is the shortest distance between them. It is also defined as the distance of the point from the line segment. Next, we'll discuss a theorem based on the perpendicular bisector of a chord. The theorem states that the perpendicular from the center of a circle to a chord bisects the chord. Now, consider a circle with a center O, such that AC is a chord of the circle. OB is perpendicular drawn from O to AC. We have to prove that OB bisects the chord AC or divides it into two equal parts so that AB equals BC. Let's join the lines OA and OC. Consider triangles OBA and OBC. Since OB is perpendicular to AC, triangles OBA and OBC are two right-angled triangles. Further, in triangles OBA and OBC, OA equals OC, since both are radii of the given circle. Note that OA and OC are also the hypotenuse of the right-angled triangles OBA and OBC. OB is common to both the triangles. So, by the RHS congruence rule, triangles OBA and OBC are congruent. Congruent triangles have their corresponding sides equal. Thus, AB equals BC. Therefore, B is the midpoint of AC. This means that line OB divides the chord AC into two equal parts or bisects it. So our theorem is proved. Now, let's see if the converse of what we just proved is also true. The theorem states that the line drawn from the center of a circle to bisect a chord is perpendicular to the chord. Consider a circle with center O and a chord AC. Let us draw a line OB so that it bisects AC. Now, we have to prove that OB is perpendicular to AC. Let's join OA and OC. Consider triangles OBA and OBC. In these two triangles, it is given that AB equals BC since OB bisects AC. OA equals OC since both are radii of the same circle. OB is common side to both the triangles. So the triangles OBA and OBC are congruent by the SSS congruence rule. This also means that angle OBA equals angle OBC since congruent triangles have their corresponding angles equal. Angle OBA and angle OBC are equal and together equal to the straight angle ABC, which equals 180 degrees. This means that angle OBA and angle OBC are both right angles. This also means that OB is perpendicular to AC. So the theorem is proved. Look at the circle. Let's draw two chords which are equidistant from the center of the circle. If you don't know the center of the circle, would it be possible to draw chords that are equidistant from the center? Yes, it's possible. Let's see how. If we measure the chords, we find both the chords are congruent. This means that the chords which are equidistant from the center will be equal in length. So even if you don't know the center, and you draw congruent chords anywhere inside the circle, they will be equidistant from the center. Based on this observation, we arrive upon a theorem. Equal chords of a circle are equidistant from the center of the circle. In the figure, we have two equal chords, AB and PQ. Let's draw perpendiculars from the center O to the chords AB and PQ. The perpendiculars are OM and ON, which also represents the distance between the center and the chords. Now to verify the theorem, we will prove that OM equals ON. A simple and quick way to do this is measure OM and ON using a ruler. First, let us measure OM. Now, let us measure ON. We can see that OM equals ON. This proves that equal chords of a circle are equidistant from the center of the circle. Here is a circle whose center is marked. Now the problem is to draw two chords so that they are equal in length. The challenge is to do it without measuring the lengths of the chord. Now, how easy is that? Actually, very easy. Let's discuss a theorem. The theorem states that the chords at the same distance from the center of a circle are equal in length. You can start by marking 2 points M and N at an equal distance from the center O. Now draw a chord AB passing through M and perpendicular to OM. Next, draw a chord PQ passing through N and perpendicular to ON. We have to prove that if OM equals ON, then AB equals PQ. Now, let us measure chords AB and PQ to see if they are equal. First, let us measure AB. Next, we'll measure PQ. Simple measurement shows that chords AB and PQ are equal. You just prove that chords at an equal distance from the center of a circle are equal in length. Do you know how we perceive sizes of different things that we see? How do we decide whether an object is larger, smaller, or equal in size to another object? This depends on the angle subtended by an object to an eye. The object that subtends a larger angle to our eye appears larger in size. If two objects subtend equal angles to our eye, they appear equal in size. Let us understand this better by using a triangle ABC. The angle at any of the vertices of a triangle is the angle subtended at that point by its opposite side. For example, angle BAC is the angle subtended by BC at point A. Angle ABC is the angle subtended by AC at point B. Angle BCA is the angle subtended by AB at point C. Consider a circle with a chord AB. If we join A and B with O, the center of the circle, then angle AOB is the angle subtended by chord AB at the center of the circle. Let us see how this angle changes if the positions of A and B change. What do we observe? As the chord AB moves closer to the center O, it increases in length. The angle subtended by AB at O also increases as the chord AB moves closer to the center O. As the chord moves away from the center, its length and angle subtended by it at the center decreases. Remember, we discussed that objects that appear in equal sizes subtends equal angles to our eye. Let us see if this is true for equal chords of a circle. The theorem states that equal chords of a circle subtend equal angles at the center. Here we have two chords AB and PQ that are equal in length. We have to prove that angle AOB is equal to angle POQ. In the triangles AOB and POQ, we know that AB equals PQ. Note that OA equals OP and OB equals OQ, since all these four-line segments are the radii of the same circle. Since corresponding sides of triangles AOB and POQ are equal, the two triangles are congruent by the SSS congruence rule. This also means that angle AOB equals angle POQ, since they are corresponding angles of congruent triangles. So we have proved that equal chords of a circle subtend equal angles at the center. Now, let us see if the converse of what we just proved is also true. Theorem states that the chords that subtend equal angles at the center of a circle are equal in length. Consider a circle with center O and two chords AB and PQ such that angle AOB equals angle POQ. Now, we have to prove that AB equals PQ. In triangles AOB and POQ, we know that angle AOB equals angle POQ. Note that OA equals OP and OB equals OQ, since all these four lines are radii of the same circle. Since two adjacent sides and the corresponding angles of the triangles AOB and POQ are equal, the two triangles are congruent by the SAS congruence rule. This also means that AB equals PQ, since they are corresponding sides of congruent triangles. So, we have proved that chords of a circle that subtend equal angles at its center are equal in length. Welcome to the lesson on arcs of a circle. At the end of this lesson, you will be able to prove that congruent arcs of a circle subtend equal angles at its center. You will also be able to prove that the angle subtended by an arc at the center of a circle is double the angle subtended by the arc at any other point on the circle, and that an arc subtends equal angles at all points on a circle in the same segment of the circle. You must have played with toy bows and arrows as a child. Here are 5 bows. Let's use these to learn more about the circles. But first, can you spot which of these are identical? Did you get it right? Yes, these two are identical. We say they are identical because when placed one over the other, they completely overlap each other. Now, let us do something much more interesting with these bows. Let's place these 5 bows together like this. What do we get? A circle. Can you see the 2 identical bows? What do they represent now? The curved parts of the 2 identical bows represent 2 congruent arcs, AB and CD, and the string of the bows represent 2 equal chords, AB and CD of the circle. We call them congruent because they superimpose each other completely. Before we move on to study a few properties of congruent arcs of a circle, let us look at the condition of the congruency of arcs once again. As you can see, here are 2 arcs from 2 different circles. They are of the same length, but they do not superimpose each other completely. This is because these arcs are curved differently. These arcs are not congruent. Now, let us return to the circle we formed. Here, if AB and CD are 2 congruent arcs of a circle, what can you say about the chords AB and CD? Simple measurement shows that AB and CD are equal in length. Thus, we can say that the chords corresponding to congruent arcs of a circle are equal. The converse is also true. If AB and CD are 2 equal chords of a circle, their corresponding arcs are congruent. Now, let us use the properties of congruent arcs of a circle to prove a theorem. The theorem states that congruent arcs of a circle subtend equal angles at the center. Now, we have to prove that if AB and CD are 2 congruent arcs, then angle AOB is equal to angle COD. To prove the theorem, let us draw corresponding chords from the arcs AB and CD. As you can see, angles subtended by arcs AB and CD at center O are equal to the angle subtended by their corresponding chords at the center. In this figure, chords AB and CD are equal since we have already seen that chords corresponding to congruent arcs of a circle are equal. We already know that equal chords of a circle subtend equal angles at its center. Thus, angle AOB is equal to angle COD and the theorem is proved. How many types of arcs do you find in a circle? A chord divides a circle into 2 arcs. The shorter arc is called minor arc, while the longer one is called major arc. If the chord is the diameter of the circle, it divides the circle into 2 equal arcs, each of which is called a semicircle. Next, we'll discuss the theorems related to arcs. The theorem states that the angle subtended by an arc at the center is double the angle subtended by the arc at any point on the remaining circle. Let us prove the theorem simultaneously for a minor arc, major arc, and a semicircle. In the given figure, we have an arc AB. Consider any point C on the circle that is outside AB. Now, here we have to prove angle AOB is equal to 2 times angle ACB. Before we start with the proof, consider a line joining point C to the center O and extend it to a point D within the circle. Consider triangle OAC in each of these figures. In each case, angle AOD is the exterior angle of triangle OAC. Since the exterior angle of a triangle is equal to the sum of its interior opposite angles, angle AOD is equal to angle OAC plus angle OCA. Also in triangle OAC, OA is equal to OC since they are radii of the same circle. This makes triangle OAC an isosceles triangle. This also means that angle OAC is equal to angle OCA since angles opposite to equal sides of a triangle are equal. This also means that angle AOD is double the angle OCA. Similarly, in the triangle OBC, we can prove that angle BOD is double the angle OCB. From these results, we get the sum of angles AOD and BOD is double the sum of angles OCA and OCB. This clearly shows that angle AOB is double the angle ACB. Thus, the theorem is proved. Please note, in case of the major arc, the reflex angle AOB will be double the angle ACB. Now consider another point D on the circle in the same segment as point C. What can you say about angles ACB and ADB? The theorem states that angles subtended by an arc at all points within the same segment of the circle are equal. So, we have to prove that angle ACB is equal to angle ADB. By the theorem, the angle subtended by an arc at the center is double the angle subtended by the arc at any point on the remaining circle. We can say that angle AOB is double the sum of either the angles ACB or ADB. Thus, angles ACB and ADB are equal and the theorem is proved. Here is an interesting property of angles formed by an arc in a semicircle. All angles formed in a semicircle are right angles. Let us try and prove this. Draw a diameter AB to divide the circle into two semicircles. Now, consider arc AB. Take a point P outside AB on the circle and join AP and BP. By the theorem that states that the angle subtended by an arc at the center is double the angle subtended by the arc at any point on the circle, we have angle AOB is equal to 2 multiplied by angle APB. Since AOB is a straight angle, we get angle APB is equal to 90 degrees. By the theorem, we also know that all angles subtended by an arc in the same segment are equal. This means that angles AQB and ARB are also right angles. Thus, we can say that all angles formed in a semicircle are right angles. Welcome to this lesson on cyclic quadrilaterals. At the end of this lesson, you will be able to define concyclic points and cyclic quadrilaterals. You will be able to illustrate that the sum of opposite angles of a cyclic quadrilateral is 180 degrees. You will also be able to illustrate that if the sum of opposite pair of angles in a quadrilateral is 180 degrees, then the quadrilateral is cyclic. Here we have three friends, A, B and C. Wherever they stand, they say that they are standing on a circle. Is this true? Let us freeze them in this position and find out. We will know they are telling the truth if we can draw a circle passing through the positions of A, B and C. Okay, let us begin with the construction. First, let us join AB and BC. Next, let us mark the midpoints of AB at M and BC at P. Now, let us draw a perpendicular at M. What does this line MN represent? MN is the perpendicular bisector of AB. Now, let us draw a perpendicular at P. Here PQ is the perpendicular bisector of BC. The perpendicular bisectors of AB and BC intersect at O. What can you say about the lengths OA, OB and OC? They are equal because any point on the perpendicular bisector of a line segment is at equal distance from the endpoints of the line segment. Since A, B and C are at equal distance from O, a circle drawn with the center O and the radius OA will pass through all the 3 points A, B and C. So, the 3 friends were right after all. Wherever they stand, a circle can be drawn passing through their positions. Points in this case, A, B and C, that lie on the same circle are called concyclic points. Can we conclude that 3 points are always concyclic? No, this does not always hold true. For example, let's consider 3 points that are collinear. A circle can be drawn through any 2 points, but the third will fall either inside or outside that circle. Based on this observation, we can conclude 3 points are concyclic only if they are not collinear. Uh-oh, we have another friend of A, B and C who wants to stand on the circle with them. Now, where should D stand? Let us find a position for D, so that we can draw a circle that passes through the positions of all the 4 friends A, B, C and D. This calls for some construction. First, let us join AB, BC and AC. Now, let us measure angle ACB. In this position, angle ACB is equal to 70 degrees. Now, we are very close to finding the correct position for D. We just find another point that makes the same angle as angle ACB with AB. In this case, we find another point that makes an angle of 70 degrees with AB, and that is where D should stand. D has found his position. Like his friends A, B and C, he is also standing on the circle. Based on the observation, we arrive upon the theorem which states if a line segment joining 2 points subtends equal angles at 2 other points on the same side of the line segment, then all the 4 points are concyclic. Let's prove this theorem. Here AB is a line segment that subtends equal angles at C and D. We have to prove that A, B, C and D lie on the circle. Let us use the construction we did earlier to draw a circle through points A, B and C. For proving the theorem, let us suppose that the circle drawn through A, B and C does not pass through D, but intersects AD at D'. If the circle through A, B and C passes through D', then angle ACB is equal to angle AD'B. This is because the angles subtended by a chord in the same segment of the circle are equal. But it is given that angle ACB is equal to angle ADB. Thus, angle AD'B is equal to angle ADB. This is possible only if D' coincides with D. What does this mean? This means that A, B, C and D are concyclic points. Thus the theorem is proved. What do we get if we join four concyclic points A, B, C and D? We get a quadrilateral ABCD. Now this quadrilateral is special. All its vertices lie on a circle. A quadrilateral whose vertices lie on a circle is called a cyclic quadrilateral. Here is a very interesting property of cyclic quadrilaterals. Let us measure the opposite angles BAD and BCD. Note that their sum is equal to 180 degrees. Now measure the opposite angles ABC and ADC. What do you observe? Their sum is also equal to 180 degrees. Let us verify the results for another cyclic quadrilateral. Next, let us measure the opposite angles BAD and BCD in this quadrilateral. Note that their sum is equal to 180 degrees. Similarly, measure the opposite angles ABC and ADC. Their sum is also equal to 180 degrees. This way you can illustrate the theorem that in a cyclic quadrilateral, the sum of opposite angles is always equal to 180 degrees. You can also illustrate the theorem that if the sum of opposite angles of a quadrilateral is 180 degrees, then the quadrilateral is cyclic. Here is a simple quadrilateral, a square ABCD. We know that all angles of a square are equal to 90 degrees. This means that the sum of its opposite angles is equal to 180 degrees. Let us see if we can draw a circle that contains all its vertices. If we draw perpendicular bisectors of sides AB and AD, we find that they intersect at a point O. If we draw a circle with center as O and radius equals OA, we find that the circle contains all the vertices of the given quadrilateral. Through simple construction, you can also illustrate that a quadrilateral is cyclic if the sum of at least one pair of its opposite angles is equal to 180 degrees.